Okay, in this lecture we're going to cover the first part of our section 2.2 material on vectors in 3 dimensions. And before we can discuss vectors in 3 dimensions, we need to discuss the 3-dimensional coordinate system, or sometimes referred to as space. So let's start with some definitions. So we'll say in order to represent points in space, we would first choose a fixed point, which we're going to label O, and refer to as the origin. And we'll define 3 directed lines through the origin, which are perpendicular to each other and referred to as the coordinate axes, and labeled as the x-axis, y-axis, and z-axis. So here in our left-hand figure, we have a central point, which is labeled O. It's referred to as the origin. And we have 3 lines, which are all perpendicular to one another, which are referred to as the x-axis, the y-axis, and the z-axis. Now, these 3 sets of coordinate axes define 3 planes in space. So we would refer to the xy, the xz, and the yz planes as the coordinate planes. So for instance, the xz plane would be the plane determined by the x and z axes. The xy plane would be the plane determined by the x and y axes, and then the yz plane would be the plane determined by the y and z axes. So we have these 3 coordinate planes, and these planes divide space into 8 octants. So when we are labeling these octants or referring to them, typically we'll only make reference to the first octant specifically. And the first octant is the octant of space where x, y, and z are all positive. So here we would have x is positive, y is positive, and z is positive. So these octants are similar to the 4 quadrants in the plane that the x and y axes divide the plane into. So in space, since we have 3 coordinate axes, we end up dividing space into 8 octants. And when we're referring to that first octant, it's the part of space where x, y, and z are all positive. So we can represent points in space as ordered triples of real numbers, x, y, and z. So just like we would represent points in the plane by an ordered pair, x, y, we can represent points in 3 dimensions or space as an ordered triple, x, y, z. And the set of all ordered triples of these real numbers is called the 3-dimensional rectangular coordinate system, or sometimes space for short. And it's denoted by R3, which refers to the set of all ordered triples x, y, z, such that x, y, and z are real numbers. So the set of all points in 3-dimensional real space. So let's look at some examples to familiarize ourselves with how to identify points in space, and then we'll derive some formulas, some geometric formulas, similar to what we have for points in the plane, but for points in 3 dimensions. So as a simple example to start with, we're asked to plot the point 1, -2, +3 in 3-dimensional space. And then we ask, what are the projections of this point onto the xy plane, the xz plane, and the yz plane? So let's start by plotting our point in three-dimensional space. So we'll start by sketching our coordinate axes. We have the x-axis, the y-axis, and the z-axis, where my arrows indicate the direction of increasing x, y, or z. So in order to plot the point 1, negative 2, 3, well, that means that our x-coordinate for this point is 1. So we're going to move 1 unit outward in the positive x direction. Y is negative 2. So along the y-axis, we're going to move 2 units in the negative direction. And then in the z direction, we're going to move 3 units upward. So to plot our point from the origin, we're going to move outward 1 unit in the x direction, and from there, we will move to the left, or in the y direction, 2 units in the negative direction. And from that point, we will move 3 units upward. So our point of interest here is this point shown in blue, 1, negative 2, positive 3. So we've plotted our point here, and the next part of the question asks about the projection of this point onto the xy plane, the xz plane, and the yz plane. So when we refer to a projection, we're thinking about sort of the shadow that this point casts onto a particular coordinate plane in space. So if we're looking at the projection down onto the xy plane, well, we see within the plane defined by the xy axes, we would have this point where our x-coordinate was 1, our y-coordinate is negative 2, and since we're in the xy plane, that means our z-coordinate would be 0. So let me keep track of this to the side. So for our projection onto the xy plane, we have the point 1, negative 2, 0. Next, we ask about the xz plane. So for our projection onto the xz plane, well, we're moving our point to this projection onto the plane determined by the x and z axes. So we would see that our projection here, well, we have an x-coordinate of 1, a y-coordinate of 0, since we're in the xz plane, and a z-coordinate of 3. So here we would have 1, 0, 3 for our projection onto the xz plane. So now, let's see what we have for our projection onto the the yz plane. So for the projection of our point onto the yz plane, we would have this point where x is 0, y was negative 2, and z was 3. So we would have the point 0, negative 2, 3 for our projection onto the yz plane. So my figure here not drawn perfectly, of course, but we can try to get a little visualization of what these projections look like. Okay. Now, a problem of interest for points in space is determining the distance from one point to another. That's a problem that will come up fairly often throughout this course. So we have the following theorem, which is a distance formula between 2 points in 3 dimensions. And it's very similar to the distance formula between points in the plane. So here's what it says. The distance between the points P1, which has coordinates x1, y1, and z1, and a point P2, which has coordinates x2, y2, and z2, is given by the square root of the sum of the squares of the differences between the x, y, and z coordinates for these 2 points. So that is the square root of the sum of x2 minus x1 squared, y2 minus y1 squared, and z2 minus z1 squared. So this is very similar to our distance formula that we had in the plane, can now just be extended to 3 dimensions. So let's look at an example of this. We're asked to find the distance between the points P1, which is 1, negative 5, 4, and P2, which is 4, negative 1, negative 1. So using our new distance formula, the distance between these points, which we refer to as d, is going to be the square root of the sum of the squares of the differences between our coordinates. So for the x coordinates, we would have 4 minus 1. We're squaring that quantity. Then we add, for the difference in our y coordinates, we would have negative 1 minus negative 5, or plus 5 squared. Plus, for our z coordinate, we would have negative 1 minus 4 quantity squared. So let's see what this gives us. Simplifying a bit, we have the square root of our first term would be 3 squared, which is 9, plus our second term would be 4 squared, or 16, plus our last term would be negative 5 squared, or 25. So summing these, we have the square root of 25 plus 25, or root 50. Now 50 is 25 times 2, so root 25 is 5, and then we've got our square root of 2. So this is the distance between those 2 points in 3 dimensions. So now, making use of this distance formula, we can ask certain geometric questions about points in space, or figures determined by points in space. So in this next question, we're asked to find the lengths of the sides of a triangle, which has its vertices at the points A, B, and C, whose coordinates are given. And then we're supposed to determine whether that triangle is isosceles, right, both, or neither. So let's start by determining the distances between these points, which will give us the lengths of the edges of this triangle. So we'll start with the distance between the points A and B. So for notation here, that distance I'm going to denote as follows. So I'll say sort of the absolute value of AB we'll refer to as the distance from point A to point B, which is given by the square root of the sum of the squares of the differences between our x, y, and z coordinates. So for A and B, the difference in our x coordinates would be 3 minus 2. We're taking that value squared. For our y coordinates, we would have 3 minus 1 squared. And for our z coordinates, we have 4 minus 0 squared. So let's see what this gives us. We have now the square root of For our difference in the x-coordinates, we add 1 squared, which is 1. Plus, for the difference in the y-coordinates, we have 2 squared is 4. And then for the difference in the z-coordinates, we had 4 squared is 16. So we're left with the square root of 21. Now for the distance from point A to point C, we will again have the square root of the sum of the squares of the differences in the x, y, and z coordinates between these points. So for our x-coordinate, we would have 5 minus 2 squared, plus for our y-coordinate, we have 4 minus 1 squared, and for our z-coordinate, we would have 3 minus 0 squared. So simplifying, we have the square root of 3 squared is 9, plus 3 squared is 9, and then plus another 3 squared is 9. So altogether we have root 27, or 3 root 3 if you prefer. And then the distance from point B to point C, so that is the length of the third leg of our triangle here, would be the square root of the sum of the squares of the differences between the x, y, and z coordinates of points B and C. So for the x coordinates, we would have 5 minus 3 squared, plus for the y coordinates, we would have a 4 minus 3 squared, and for our z coordinates, we would have 3 minus 4 squared. So this gives us a 2 squared, or 4, plus 1 squared is 1, and then plus 1 squared is 1, so we're left with root 6. So we have the lengths of the sides of this triangle, ABC, and then the second part of the question asks us to determine whether this triangle is isosceles, right, both, or neither. So let's start with the first question. Is this triangle isosceles? We'll recall an isosceles triangle has 2 sides that have the same length. So looking at the lengths of our 3 sides, we see that none of them are equal to one another. So it cannot be isosceles. So let's start by saying this is not isosceles. Now the next question is whether this is a right triangle. So how can we determine if a triangle is a right triangle? Well, any right triangle has to satisfy the Pythagorean theorem. So that is the sum of the squares of the lengths of our 2 shorter sides of the triangle must equal the square of the length of our hypotenuse. Now looking at the lengths for the sides of our triangle, we can see pretty quickly that if we were to take the length of AB squared, 21, plus the length of BC squared, which is 6, we would have 27, which is the length of AC squared. So this is a right triangle. So it is not isosceles, but it is a right triangle. Since the length of AB squared plus the length of BC squared is equal to the length of AC squared. So certainly it is not both nor neither, but we found that it is not isosceles, but it is a right triangle. So this distance formula can be used to provide some insight about different types of figures in three-dimensional space. Now the next type of figure that we'll talk about in 3 dimensions is the analog of a circle in 2 dimensions. So that analog in space would be a sphere. So the following theorem is going to define the standard form for the equation of a sphere. So here's what it says. An equation of the sphere, which has its center at a point x naught, y naught, z naught, with radius r, is given by x minus x naught squared plus y minus y naught squared plus z minus z naught squared is equal to r squared. So it's very similar to the equation of a circle in 2 dimensions. Now we just have some z component. And this formula for the equation of a sphere follows directly from the distance formula. So let's think about how a sphere is defined. So a sphere would be defined as the set of all points which are some common distance from a center point. And that distance from the center of our sphere to any point on the sphere is what we refer to as the radius. So a little scratch work here, we can say if we have any point x, y, z is a point on the sphere that has a particular radius, let's call it r, then the distance from this point x, y, z to the center x naught, y naught, z naught is found by taking the square root of the sum of the squares of the differences between these coordinates. So we would have x minus x naught squared plus y minus y naught squared plus z minus z naught squared. So that's the distance from any point on my sphere to the center, and this is what we call the radius of our sphere, the distance from the point or from some point on the sphere to the center. So if we simply square both sides of this equation, we can see that we obtain the given formula for a sphere. So let's look at an example making use of this formula. In this first problem, we're asked to find the equation of the sphere whose center is 5, 3, 2, and which has radius 3. And then we ask ourselves, what is the intersection of this sphere with the xy plane, the xz plane, and the yz plane? So let's find the equation of this sphere first. So here we were given the center and the radius, so substituting directly into our formula for the equation of a sphere, we would have x minus 5 squared plus y minus 3 squared plus z minus 2 squared is equal to the radius squared. Our radius was 3, so 3 squared gives us 9. So this is the equation of that sphere. And the next part of this question asks about the intersection of this sphere with the xy plane, the xz plane, and the yz plane. So let's start by looking at the intersection with the xy plane. Now, we know for any point in the xy plane, our z-coordinate must be 0. So to find the intersection of this sphere with the xy plane, we're going to let z equal 0 in the equation of our sphere. And we have our equation as follows: x minus 5 squared plus y minus 3 squared plus, when we substitute z equals 0 into this equation for our sphere, we would be left with just negative 2 squared is equal to 9. So we have x minus 5 squared plus y minus 3 squared plus 4 is equal to 9, or moving all of our constants to one side, we would have 9 minus 4 is 5. So let's think about what this equation represents geometrically. We would recognize this as the equation of a circle with center at the point 5, 3, and radius square root of 5. So that's saying if we're thinking about slicing our sphere through with the xy plane, we would get a circle. And that sort of makes sense. In some cases, if we're slicing a sphere through with a particular plane, well, we would expect to see a circle for that cross section. So let's look at some of the other planes. For the xz plane, well, for any point in the xz plane, we're going to let y equal to 0. And so the equation of our sphere becomes x minus 5 squared plus negative 3 squared plus z minus 2 squared is equal to 9. So again, grouping our constants, well, on this left-hand side, we would have negative 3 squared, which is 9. We had 9 on the right-hand side, so if I subtract 9 from both sides, I would have x minus 5 squared plus z minus 2 squared is equal to 0. So a couple of ways we could think about this. This is sort of like the equation of a circle, which is centered at 5, 2, but would have radius 0. So what sort of object would that be describing? Well, it would describe a single point in the plane. So a circle of radius 0 we could think of as a single point. What would be the point we're referring to here? Well, the center of our circle, which would be 5, 2. So here our intersection would be a point, in particular the point 5, 2. And for the last part of this question, we're asked about the intersection of our sphere with the YZ plane. So to find that intersection, we're going to let our x-coordinate equal 0, since for every point in the YZ plane, x must be 0. And we have a negative 5 squared plus y minus 3 squared plus z minus 2 squared is 9. So simplifying a little bit, we've got 25 plus y minus 3 squared plus z minus 2 squared is 9. Or moving all of our constants to one side, y minus 3 squared plus z minus 2 squared is negative 16. So what we have here is an equation which says the sum of two terms squared would have to equal a negative number. But we know that when we square any quantity, it has to be non-negative, so there are no values for y and z that would satisfy this equation. So we would say there is no intersection between the YZ plane and this sphere. So that is, the sphere does not cross the YZ plane in space. Okay. So let's look at another example involving spheres. Our next example is to find the equation of a sphere which is centered at 1, 2, 3 and passes through the point negative 1, 1, negative 2. So in order to find the equation of a sphere, we said we need two things. We need the center of our sphere and its radius. Now, in this example, we're given the center of our sphere. Now, we need to find the radius. So what we're told here is that this sphere must also pass through this particular point. So how can we use that to find our radius? Well, we know that the distance from the center of our sphere to any point on that sphere must be equal to the radius. So here, we're going to let the radius, r, of this sphere be the distance between my center and this point on the sphere that we're given, which would be found by taking the square root of the sum of the squares of the differences in the x, y, and z coordinates for these points. So for our x coordinate, we would have a -1 minus 1 squared plus a 1 minus 2 squared plus a -2 minus 3 squared. So simplifying a little bit, we have the square root of -2 squared is 4, plus -1 squared is 1, plus -5 squared would be 25. So altogether, we would have root 30. So now that we have the radius and the center of our sphere, we can substitute the values into the equation of a sphere, and we would have x minus the x coordinate for the center was 1. We square that value. Plus y minus the y coordinate for the center was 2. We square that value. And then plus z minus the z coordinate, which was 3 squared, is equal to the radius squared, which would be 30 here. So we have the following equation for that sphere. So let's look at another one. In this next example, we're given some quadratic equation in terms of x, y, and z, and we're asked to show that this equation represents a sphere and then find its center and radius. So much like we did for quadratic equations in terms of x and y, we could maybe group the variables x and y and complete the square in each quadratic in order to show that we might have a circle. So we're going to use the same approach here to show that this equation defines a sphere. We need to write it in the standard form for the equation of a sphere to see that it does represent a sphere and find that center and radius. So let's start here by grouping our x, y, and z variables together. So grouping the terms involving x, on this left-hand side, I would have an x squared minus 6x. Now, to that, I'm adding, let's group my y terms. I had a y squared plus 8y. So grouping those y variables together, we have that. And then plus grouping our z variables, we had a z squared minus 4z. And then that's equal to this constant 20. So now let's complete the square in each of these quadratics with respect to x, y, and z. So for the x quadratic, we have x squared minus 6x. And to complete the square, the constant I need to add is half of the b coefficient for this x quadratic, which would be -3 squared, which would give me a positive 9. Then for my y quadratic, I have y squared plus 8y. Taking half of that b coefficient for the y quadratic, I would have 4. Squaring that is 16. And then plus for my z quadratic, I have z squared minus 4z Taking half of that -4, I have -2 squared is 4. So that's what I want to add to that z term. Now this is equal to, well, we had a constant 20, but on the left-hand side, I added a 9, a 16, and a 4. So I added a total of 29 on that left-hand side of the equation. So in order to make this equation valid, I must also add 29 to the right-hand side. So let's see what this gives us. So our quadratic in terms of x, we can now factor as x minus 3 quantity squared, plus for the y quadratic, we can factor this as y plus 4 squared. And for the z quadratic, we would have z minus 2 squared is equal to, we're left with 49 on that right-hand side. So we can see that this equation is the same as the standard form for the equation of a sphere. So here we do indeed have a sphere with a center given by the point 3, -4, 2, and whose radius is 7. So our right-hand side, remember, for the equation of a sphere is the radius squared. So the square root of 49, which is 7, would be our radius here. Okay. So this illustrates how to show that a equation involving quadratics in terms of x, y, and z may represent a sphere. So the next thing we'll talk about is a formula for the midpoint of a line segment between 2 points in space. It's very similar to the midpoint formula for points in the plane. So we have the following theorem, which is our midpoint formula, which says that the midpoint of the line segment from one point, x1, y1, z1 in space, to the point x2, y2, z2, is the point whose x-coordinate is the sum of the x1 and x2 coordinates over 2. The y-coordinate would be the sum of the y1, y2 coordinates over 2. And the z-coordinate would be the sum of the z1 and z2 coordinates over 2. So that is, our coordinates for this midpoint are the average of the x, y, and z coordinates for these 2 points. So let's look at an example involving this midpoint formula. So here we're asked to find the equation of a sphere whose diameter has endpoints of 2, 1, 4 and 4, 3, 10. So there's 2 things that we need to find for the equation of a sphere. We need the center of the sphere and the radius of the sphere. Now, how can we find that here? Well, we're given the diameter or the endpoints of one diameter of this sphere. So if we look at the midpoint of the line segment connecting those 2 points, that would be the midpoint of the diameter of our sphere, we would have the center of our sphere. So let's start by finding that center. So the center of our sphere is going to be given by the midpoint of our diameter. Now to find the midpoint, we would take the sum of the x-coordinates, 2 and 4, over 2, the sum of our y-coordinates, which would be 1 and 3, over 2, and the sum of our z-coordinates, 4 and 10, over 2, which would give us, for the x-coordinate, 6 over 2, or 3. Y-coordinate would be 4 over 2, which is 2, and then 14 over 2, which is 7. So we have the center of our sphere. Let's think about how to find the radius. So the radius could be calculated in a couple of ways here. We could either find the distance between the 2 points which form the diameter of our sphere and then halve that distance, because the radius is half the distance of half the length of the diameter. Or we could take the distance from our center that we just found to either of the endpoints of this diameter. That would also give us the radius. So either approach we want to use, I'm going to find r as the distance from my center point to this first endpoint of my diameter. So that would be given by the square root of the sum of the squares of the differences in our x, y, and z coordinates. So for the x coordinate, we would have 3 minus 2 squared, plus for the difference in the y coordinates, we would have 2 minus 1 squared. And for the difference in the z coordinates, we'd have 7 minus 4 squared. So we're left with the square root of 1 squared, which is 1, plus 1 squared, which is 1, plus 3 squared is 9. So altogether, root 11. So we're then ready to find the equation of our sphere as x minus the x coordinate for the center, which is 3 squared, plus y minus the y coordinate for the center, 2 squared, plus z minus the z coordinate of the center, which is 7 squared, is equal to the radius squared, which would be 11. So we've got the following equation for our sphere. So we can see one application here of this midpoint formula. We'll look at a few applications over the period of this semester. So the last thing that we'll talk about for today's lecture is looking at some simple graphs of equations in 3 dimensions instead of in 2 dimensions. So let's start by making note of something. We know that in 2 dimensions, the graph of some equation involving the 2 variables x and y is some curve in R2, so a curve through the plane. Now in 3 dimensions, the graph of an equation involving 3 variables, x, y, and z, is in general a surface in R3, or a surface in space. So we're going to consider the graphs of some simple surfaces defined by equations. So here we're asked to describe the following regions in the indicated dimension. And in part A, we're given an equation y equals 2. We want to know what that equation describes both in R2, that is in the plane, and in R3, in space. So let's start by describing what it is in the plane. So in 2 dimensions, R2, the equation y equals 2 is a horizontal line passing through the point 0, 2. So in 2 dimensions, we would have a xy plane, and the equation y equals 2 means we have a constant value of 2 for y. So we would have this horizontal line passing through the point 0, 2. Now let's think about what this represents in space. So in R3, what does this constant value of y represent? Well, this would represent a plane which is parallel to the xz plane, passing through. Y equals 2, so the point 0, 2, 0. So if we think about this in 3 dimensions, let's see if we could get a rough sketch here. We have our x-axis, our y-axis, and the z-axis. So the constant value y equals 2 means that we would be looking at all points for which y has a constant value of 2, but of course x and z could extend infinitely in any direction. So we're talking about a plane here which lies 2 units directly to the right of this x z plane. So we have here a plane which is parallel to our xz plane 2 units to the right in space. So we can sort of generalize our discussion for this example in part A. If we were to have, let's say, a constant value of x, let's say like x was equal to -3, then we would be looking at a plane which is parallel to the yz plane and 3 units along the negative x-axis. Similarly, if we had a constant value of z, let's say z equals 1, we would be looking at a plane which is parallel to the xy plane, but lies 1 unit above that xy plane. So constant values for x, y, or z in space will define planes parallel to one of our coordinate planes passing through a given intercept. So let's look at another example. In part B, we have an inequality. X squared plus y squared is less than or equal to 1, and we want to know what that represents both in R2 and in R3. So let's start with in the plane. In R2, this inequality represents a circular disk centered at the origin, 0, 0, of radius 1. So here, if we think about our inequality, if we were to look at the equation x squared plus y squared equals 1, that would be defining a circle centered at the origin of radius 1. And since this is an inequality, x squared plus y squared is less than or equal to 1, we would be looking at all points xy on circles of radius less than or equal to 1. So we would be considering everything inside of that circle, which would give us a disk. So in this case, x squared plus y squared equals 1 would give us the equation of this circle. If we make this an inequality less than or equal to 1, well, we're looking at all points that would lie inside of this circle. Now let's think about what this represents in space. In R3, we would have a closed cylinder, closed circular cylinder to be more precise, of radius 1, centered along the z-axis. So in 3 dimensions, well, we have our x, y, and z-axes. So if we have the inequality, x squared plus y squared is less than or equal to 1, well, in the xy plane, we were talking about this disk, But if we're referring to this inequality in space, well, we're looking at equations that lie inside of this disk, but where z could take any value. So this disk is being extended along the z-axis, because z could be any value. And we see here that we would have this circular cylinder centered along the z-axis of radius 1. So let's look at our last example. In part C, we have the equation yz is equal to 0. We want to know what that represents in space, R3. Now looking at our equation, if y times z is equal to 0, then either y is equal to 0 or z is equal to 0. Now we had said from our discussion in part A, if we have a constant value of y, we're looking at a plane which is parallel to the xz plane, passing through a given value, in this case y equals 0. So this equation y equals 0 represents specifically the xz plane itself. It's the plane parallel to the xz plane, which passes through the origin, which is the xz plane. Now our second part of this equation, if z is equal to 0, well, that's referring to a plane parallel to the xy plane and passing through the origin, which would be the xy plane itself. So this equation in R3, we have the union of the xz plane and the xy plane. So here, to visualize this a little bit, we have, well, our x-axis, y-axis, and our z-axis. And the equation y equals 0 is defining the xy plane. So here we would have all of this xy plane together with, so another way to satisfy this equation was to take z equals 0, which was the xy plane. So taking together all of the xy plane, we would have the union of those two planes as the surface, which is satisfied by this equation in space.